Yeah.
All right, I really, really recommend playing this game a little bit more. If you like a challenge, this is a good challenging game to choose as your final project. If you don't like a challenge and you're waiting to choose a game, beware because the easier games are being picked up already. So you might be left with Go.
I have a question. So, what kind of games you can play? Does it have to have a winner?
It has to be a combinatorial game or some of the games we covered.
So,
It has to be a two-player game.
two-player game.
Right, you can watch the video on the definition of combinatorial game.
Oh, did I press replay?
Oh, it's in your book too. The definition.
We didn't, or he did?
Don't tell me we need to have pop quizzes on definitions in here.
Wait, I'm confused. He didn't take a piece of mine, and I still lost by 30 points. Yeah, but what about the one?
Oh, because he doesn't take the ones that he knows he's gonna get. So,
So they just gotta pass 4 times. Like, I can't make any more moves.
yes, if you can't make any more moves, you've lost.
But they pass 4 times in a row. That should be illegal.
It should be game over
I won.
because they can't move anymore. Is that right?
Yeah.
Yeah, I don't know how that's set up. So there's different rules that different organizations have. If you go look online about the game Go, you'll find that they have different rules. I was going by the rules that were in the mathematical books. So let's close laptops. Pay attention. This is actually going to be a little bit more difficult. There's several questions about Go that are mathematical. But before we start the game, is it a combinatorial game? Here's your chance to listen, Teresa.
I know
Open
what
up.
it was. I was making sure.
Huh?
I was just asking to make sure.
Is it a combinatorial game?
Yeah.
What's the criteria for a combinatorial game?
Can't be a tie.
It can be a tie.
Can't be chance, so it's a game of no chance. 2 players. How do you win the game?
Without the
So the player has no move left.
Yes, the next player can't make a move, right? So that's how you win the game. So there's 7 total properties, right? So you look at all the properties and answer the question of whether this is a combinatorial game or not.
But does the pass mean anything?
Huh?
Because if he can't move, can he just pass?
No, he can't. That's what we were trying to figure out with the online game, how it works. So I don't think this is a combinatorial game. Check all the rules and see if it is. The complexity is a question that's often asked. And so what do we mean by complexity and how do we compute it? These are some of the things I want to cover. You usually get to see these kind of ideas in a computer science class, an upper level computer science class. What we talk, these are concepts known as NP hard and NP complete. So I'm going to bring that into here, not this session, but the next session we meet. And we can also first ask a very simple question. How many positions are legal? So as you were playing the game, what you notice is sometimes you couldn't put a stone on a certain place because that move doesn't end up being legal anymore. Because if you put the stone there, you either will lose it automatically, so it's a suicidal point. They don't allow you to put down the suicidal point. Or it could be infinitely repeating points. I'll show you an example of that. So this is a 5x5 board that most of you are playing on. Some of you dare to choose a larger board to play on. Each of these corners has 3 possibilities. It could be empty, it could be black, or it could be white. So each spot has 3 potential fills. So one thing that you could do is say, well, I'm not going to actually calculate for you the amount of legal moves, but I know at maximum the total number of moves I have. So by discounting them, each point has a 3 possibility, and so I end up having 3 to the 5th times 5 total possibilities because there's 5 positions on each of the points that we have. Where does that come from? That comes from something known as the multiplication rule that you learned in probability class. But I laid it out like this, and you can actually count them up. So the upper bound is 3 to the 25th. So there's a lot of possibilities if you just brute force, say, I'm just going to look at anything. A lot of those end up not being legal. This is just an upper bound. So I know it couldn't be worse than this. Some of them end up being non-legal. So now we're heading towards your game, right? When we were talking about corners, we were talking about the fact that, well, I can't just count everything because what if there's something in the way? I can't just do that particular move. So here we're ending up in the same kind of concept. But this also includes all the illegal moves. Like if you're surrounded by black, you can't put a white piece in the center because that white piece will be taken. So that's not a legal move. Recall that a position is legal if every string of connected stones of the same color has an empty point attached to it. You need somewhere to place it. Otherwise, you're not going to have that. So by brute force, people have computed the legal moves. For example, on a 4x5 board, the legal moves is this huge number to the right. You could just have a computer crank it out. So that's not possible for an arbitrary size board. You can't do that. And there doesn't appear to be a pattern. So how do we go about thinking about this question mathematically? Well, the first thing is that you want to use mathematical notation to understand how to place it. This is where we were at with your game. How do we think about this mathematically? You already know how to play it. You need to somehow move towards symbols that you can play around with. So really, a position on an n by n board, it's a mapping from the set of points where the first comes from the rows, so each of the grid points can be labeled, and the second comes from the columns to the set of colors, white, black, or empty. So for example, this is what I mean. For example, if I label each one of the points, this is the 0th row, 1st row, 2nd row, 3rd row, and I can label the columns, then this point over, I could start looking at different points. For example, that point over here is the ordered pair 1, 2. So they're basically thinking of the game board as a Cartesian map. And that's exactly how you need to think of the corners game, as a Cartesian map. So I'm talking about the corners game a lot because there's actually a group in here playing this and doing this for their final. And we don't have, maybe I'll go get some markers. Actually, you guys could take the board, and then one person maybe could use markers and explain. So what I'd like you to do now is just turn around to the rest of the class, explain your game.
All right.
You're going to have to do it on YouTube anyways. It's a dry run, right?